Okay, so we have already sort of talked about the first point before, that the other laws, Boyle's, Charles, Gay-Lussac's, the combined gas law, even Dalton's law, they could develop hypotheses about the behavior of gases, which was easy to predict without knowing anything now about particles, molecules, entities, anything like that. So again, even Avogadro as well, even though we talk about Avogadro's number as the number of particles in a mole of something, even he didn't know. So he did really simple experiments and said that the equal volumes of gas at the same temperature and pressure should contain the same number of molecules. But he didn't even really know how to quantify the number of molecules. So then again, the law eventually was manipulated to include how many moles. So mathematically, the volume of gas and the number of moles of gas present are directly proportional if temperature and pressure are constant. So even though these questions won't be on the exam, they're actually really straightforward. So if you want to fill your note in so that it's complete, so you have, it's direct. If you have a certain amount of moles and you increase it, the volume should increase as well. So this is a simple relationship like Charles and Gay-Lussac's. Yes? Yes. It'll give you percent for how much better you'll do on the exam. I'm going to post the solutions today. Okay, so the most difficult kind of question would be something more like this, where it tells you a gram amount, so you have to find moles first, okay? Then you do the same thing. It says you add this amount of moles, so you just have to add them. But it's the same idea. If you increase the number of moles, then the volume should increase. Or vice versa, if you decreased it, then it would decrease. Okay, so this this law is the one that's going to be on your exam, and it's on the formula sheet as well. Okay, so what happens when you have a gas and you have an amount of that gas in moles? So gases are often involved in reactions, which means if you have an amount in moles, then you can do stoichiometry with that. So this would be used instead of Avogadro's law if temperature and pressure were involved. And what happens is sometimes when you have a mathematical relationship, there is a constant value that continuously shows up in your calculations. So this year we'll use KPA. Again, if you take upper year chemistries and stuff like that, we usually use atmospheres, so the R value is a little bit different. It is a reference value. It would be in a normal semester even on the back of your periodic table. So it is back here for you to use. The good thing about the R value, it's incorporated in the relationship, and the units, which are given on the back of the periodic table, help you decide what your pressure, volume, and temperature units have to be. So it says liters, which means volume has to be liters, KPA, so you might have to change pressure into KPA, moles, and Kelvin, okay? And this is based on the R value is based on the behavior of a gas when you have 1 mole. So 1 mole of an ideal gas takes up 22.4 liters, represented by that black box there. So it is a verifiable idea. And of course, we already talked about that standard pressure was 101.3 kPa and 0 degrees Celsius or 273 Kelvin. So when you sub those numbers in, you get this reference value every single time. So when you do the calculations, then you need that value as part of it. So this question, the good thing about it is that it actually, this part here, we're going to write a reaction, we're going to write the formula for nitrogen gas, we're going to do stoich, so it kind of reviews a whole bunch of topics that are important, okay? So a container contains 1.45 gram sample of nitrogen gas at a pressure of 450 torr and 22 degrees Celsius. So first of all, you need to remember that nitrogen gas is diatomic, so the I-bring clay for our new home. So its formula is N2. And we're given grams, and so in order to use the only gas law that has pressure, volume, temperature, and an amount is PV equals nRT. So we need to change this into moles. We can't have torr, you have to have kPa. You can't have degrees Celsius, you have to have Kelvin. So this question, we're going to do it all. So again, that's one of the good things. People are like, oh, the R value, but it's really referenced. It's on the back of the periodic table. You don't need to memorize it. And it tells you. So liters, we're solving for volume, so our answer will be in liters. It tells us kPa. Is this kPa? No. It tells us moles. Is this moles? No. And it tells us Kelvin. So we're going to do everything. It doesn't really matter what order you do it in. We can just go in order, like the grams are first, so let's change those to moles first. But remember, since it's diatomic, then it's going to be not just 17, or 14, I mean, it'll be 28. If you want to remind yourself, you could even put over here P, T, V, I guess. So pressure is given as torr, which we don't want. We want kPa. So how many kPa? And again, it's on the back of here, right? We have 450 torr. So on the back of the periodic table, the conversion is 101.3 kPa for 760 torr. And then you decide how you want to solve that. So you can do 101.3 divided by 760. Or you can cross multiply. You could do x times 760 equals 450 times 101.3. You should get the same answer. And then temperature. Oops, that's not what I want to do. And this formula is actually on the formula sheet as well. You just have to add 273. Not every single question makes you change the kPa, makes you change the temperature, makes you find the moles first. So you just have to read carefully what you're given, look at the R value and the units, and just check that they match. We're looking for volume. You guys might have more room than me, but now I'm squishing. You can include the units and do dimensional analysis like we've done before. You can do this all as one step if you have a good relationship with your calculator. So this is like number 3 on the exam review. So this isn't any stoic yet. Okay, so when we go through the test, I'll talk about the solutions test, those applications. But part B is a stoich application, okay? So this can be one of your choices if you would like. And then again, the other two are from the solutions unit, titration, stoich, or dissociation. Okay, so it says if the sample in A, so nitrogen, reacts with oxygen, and it makes NO2, so we should balance this. There's two N's and only one. And you need two O's. So it's going to literally say, stoichiometry is an application, blah, blah, blah. Choose one of the following. If you do a ratio that has the same coefficient, then that doesn't, why would I do that? It's not showing me that you know how to use stoich. If you don't do stoich, then under the heading that says stoich, okay, maybe that's a problem too. So really make sure that when you're doing these questions, that you are using stoichiometry. For example, on Fridays or Thursdays open book test, you wrote the dissociation equation and then never used it again. That doesn't make any sense. Why would I do that? So I just wrote stoich on your sheet. So make sure that if you want that to be one of your choices, that you know how to do that. Okay. So this time we have sample reacts with oxygen, producing NO2 in a 5-liter container at 22 degrees Celsius. It happens to be the same temperature. I'll show my conversion again, but it is the same temperature. You wouldn't need to. This time we're looking for pressure. It says the sample in A, so we can use that amount of moles. If you choose to sort of follow the format we've used before, putting the information under the substance that it goes with, so that is the 0.0518 is the moles of N2. But again, it will say stoichiometry is an application, blah, blah, blah. It's going to tell you that you have to use stoichiometry. Unlike before, where you would have had to read this question and say, okay, the sample in A is N2. Now I'm looking for NO2. Those are not the same. So you would have to do stoichiometry. Because so in order to use the ideal gas law, we have temperature, we have volume, we always have R. But if we're looking for pressure, then we need moles. So we need to change the moles of N2 into the moles of NO2, as always, using stoich. And again, I wouldn't choose 2 and 2, right? I would choose different coefficients. So I've given information about N2 and asked you about NO2 on purpose. They do not have the same coefficients. Are their coefficients very complicated? No, but they're still not the same, okay? So you can choose to write it out fully like 2 coefficient, but if you don't, if you just write the 2, I would accept that. That's okay. So then to solve for x, because the coefficient is 1, you're really just multiplying. So again, these questions are going to be under their own heading, like stoichiometry applications. So don't forget, once you do the stoich, that's part of it, but then you have to apply it to either the gas law or whatever, okay? Concentration, titration, whatever it is, okay? So now we have all the information we need. I'm kind of out of room, but the R value's always the same, okay? So if you guys have a bit more space, if you want to write it again, or you don't have to. This time we have Kelvin, we have liters. Liters, Kelvin, we're good, and we're going to solve, and our answer will be in kPa. Sort of out of room. So you would divide by 5 to get P by itself. Again, you could do that all as one step. Yes? I plugged in the volume, PV, P times V, and 5 is the volume.